Piping failure case studies, learning from real industries incidents. Good day, everyone. Welcome to this technical session on piping failure case studies presented by URGS International Engineering Services Private Limited. Piping systems are the lifelines of process industries such as oil and gas, petrochemical plants, refineries, power plants, and chemical facilities. They transport fluids under varying conditions of pressure, temperature, and flow. Despite careful design and engineering, piping failures still occur in many industrial facilities. These failures may lead to production losses, safety hazards, environmental damage, and expensive shutdowns. Understanding why piping systems fail is extremely important for engineers involved in design, maintenance, inspection, and plant operations. In this session, we will discuss common causes of piping failures, real industrial case studies, failure analysis approach, engineering lessons learned, preventive measures. Let us begin by understanding why piping failures occur. So first is importance of piping integrity. In any process plant, piping networks can extend for several kilometers. These systems are designed according to international standards such as ASME B31 codes. However, during plant operations, piping systems experience various stresses such as internal pressure, thermal expansion, external loads, vibration, corrosion, flow-induced forces. If these factors are not properly considered or controlled, they may result in piping failures. Maintaining piping integrity is therefore critical for plant safety and reliability. Now let us look at some common piping failure mechanisms. So now let us see common piping failure mechanisms. Several mechanisms can lead to piping failure. The most common ones include corrosion failures. Corrosion is one of the most frequent causes of piping failures. It may occur due to chemical reactions with process fluids, presence of moisture or oxygen, inadequate material selection, poor corrosion protection. Types of corrosion failures include uniform corrosion, pitting corrosion, stress corrosion cracking, erosion corrosion. Over time, corrosion reduces pipe wall thickness and may eventually cause leaks or ruptures. The second cause is thermal expansion problems. Piping systems carry hot fluids experience thermal expansion. If expansion is not properly accommodated through expansion loops, flexible supports, proper routing, then excessive stresses can develop in the piping system. This may lead to pipe deformation, support failures, equipment nozzle overload, pipe cracking. Then third is vibration-induced failures. Vibration is another significant cause of piping damage. Sources of vibration may include pumps, compressors, flow turbulence, two-phase flow. Continuous vibration can result in fatigue failure of pipes, supports, and weld joints. Then fourth is fabrication and welding defects. Improper welding procedures, poor workmanship, or lack of quality control can introduce defects such as lack of fusion, porosity, cracks, incomplete penetration. These defects may grow over time and eventually lead to failure. Then fifth is improper support design. Pipe supports play a crucial role in maintaining piping stability. If supports are incorrectly located or designed, they may cause excessive stress in piping, sagging or displacement, load transfer to equipment nozzles. This can lead to long-term structural damage. Then section 3 is case study 1, corrosion failure. So let us examine a typical corrosion failure case. In a petrochemical plant, a carbon steel pipeline carrying process fluid developed a sudden leak during operation. Upon inspection, it was observed that the pipe wall thickness had significantly reduced due to internal corrosion. Root cause analysis revealed that the process fluid contained corrosive components. The material selection was not suitable for the service conditions. Corrosion monitoring was not properly implemented. So what lessons learned from this case? It includes proper material selection is essential. Corrosion avoidance must be considered during design. Regular inspection and thickness monitoring are necessary. Then next is case study is thermal expansion failure. In another industrial facility, a high temperature steam line experienced cracking near a welded joint. Investigation showed that the piping system did not include adequate flexibility to absorb thermal expansion. During startup and shutdown cycles, repeated expansions and contraction created high stress in the weld area. Eventually, the pipe developed a fatigue crack. The corrective actions included redesigning the piping layout, adding expansion loops, installing flexible supports. Then the case study third is vibration failure. In a gas processing plant, operators noticed abnormal vibration in piping line connected to a compressor. So after several months, the pipe failed at a support location. Detailed analysis showed that flow-induced vibration was present, support spacing was too large, fatigue damage accumulated over time. So solutions implemented included additional adding additional supports, installing vibration dampers, conducting vibration analysis. Similarly, section 6 is for failure investigation methodology. So when a piping failure occurs, engineers follow a systematic investigation process. So what are these? First, visual inspection means examine the failed component for signs of corrosion, cracking, deformation or erosion. Then second is data collection. Here we have to gather operating conditions such as pressure, temperature, flow rate and vibration data. Then third is material analysis. Perform laboratory tests such as metallurgical examination and chemical analysis. Then after that, stress analysis means evaluate stresses in the piping system using engineering calculations or simulation tools. Then root cause identification. So here we have to determine the fundamental cause of the failure. Then at last, corrective and preventive actions means implement engineering solutions to prevent recurrence. Then section 7 is for preventing piping failures. So some key practice include how can we prevent this piping failures. Preventing piping failures requires a proactive engineering approach. What are those? Proper piping design according to ASME codes, accurate stress analysis during design, appropriate material selection, adequate pipe supports and flexibility, corrosion monitoring programs, regular inspection and maintenance, vibration monitoring, proper welding and fabrication procedures. When these practices are implemented effectively, piping reliability significantly improves. At last, piping failures can have serious consequences, including safety hazards, environmental impact, and financial losses. However, most failures are preventable when engineers apply sound design practices, perform proper inspections, and learn from past incidents. By studying real piping failure case studies, engineers can better understand the risks and develop more reliable piping systems. Thank you for attending this session. So for professional training programs on piping engineering, failure analysis and reliability engineering, you may contact us. We have weekend and evening batches for working professionals every month. Contact URGS International Engineering Services Private Limited. Our email ID is info@urgseng.com. Mobile number is +91 73 59 45 8455. Thank you and have a great day.